Correlation is a term that's used a lot, and it's worth noting a few points to keep in mind for when you use it or when you read about it being used by other people. So let's start with an example. If you look at the population of children in the United States and you look at reading ability and shoe size, so your population is children kindergarten age to high school age, say 5 through 18, and you're looking at reading ability measured by some test and shoe size, you're going to find a positive correlation. So the bigger the shoe size, the better the kid can read. And so if you are talking to a child and that child is having difficulty reading, then should you go out and buy them bigger shoes? No, I don't think so. And you're not going to do that because it's not the shoe that helps the kid to read. What you're noticing, of course, is that older children both have bigger shoes and they can read better in general. And so even though you are seeing a relation between the shoe size and the reading, it's not that one of those variables causes the other to increase. So the way we say it is that association is not causation. Just because two variables are related, that doesn't mean that one is causing the other. And that is apparently an obvious thing when it is pointed out in this way, but it is very often forgotten. So important to keep in mind that, if two things have a correlation of 0.8 or 0.9, great. Then as one increases, the other one does increase. You've established that, but you have not established why. Another thing to keep in mind is that the correlation measures linear association. We've said that a few times. Now take a look at this scatter diagram here, and it seems to me that we've got this nice little quadratic curve going. That's not linear. However, it's a very clear relation. These two variables are definitely associated, but they are not linearly related, and so if you calculate the correlation, you're going to get something close to zero. I think you get something slightly negative because there's this high bit here, and so there's a little bit of a negative trend, but so close to zero as makes no difference. And so you should not use R when describing these data. It's as simple as that. R measures linear association. I don't think anybody cares whether this curve looks as though it's clustered about a straight line. So we just don't use it. One of the things I've noticed, and maybe this is a Californian thing, is people use the word correlated just in ordinary English. So people will say, oh, those two things aren't correlated at all. And I'm thinking, really? What exactly do they mean there? Because typically they mean those two things aren't related at all. But they say correlated, which is much weaker, because correlated means linearly related. And so if two things aren't correlated, then they aren't linearly related, but like this, they may be strongly related in some other way. So when people in ordinary English say, oh, those two things aren't correlated, what they really want to say is those two things aren't related. And I'm wondering why they sort of mess themselves up by using the word correlated. And in the end, after thinking about it, the conclusion I've come to is if you use one more syllable, then you sound more educated, and that's why people use more syllables. But really, related is a very good word. It carries the meaning that the people are trying to express. And we as statisticians are going to be very careful about using the word correlated, because it measures a very particular kind of association, namely linear. And while we're on this subject, there's another kind of scatter diagram which we need to be careful about, and that's the one with outliers. Even a single outlier can have a big effect on R, and the best way to see it is by playing with outliers on one of the applets in your textbook. So here is a scatter diagram, and I'll remind you that this red point is the point of averages, average x and average y, and it has 100 points on it. Those fill up the screen a bit, so I am going to reduce the number of points to 10, and there I have a scatter diagram with 10 points, and the correlation is exactly 0 by construction of the applet. And so what I'm going to do is I'm going to take this scatter diagram, which the calculation decides has no linear relation, and I'm going to try and convince it that it has a linear relation by adding just one point. And the point I'm going to add is right here. There. That's my point, and look what happened to the correlation. It went from 0 to 0.24, and on a scale of 0 to 1, that's a massive change. Just this single point makes it look like there's a linear trend. One point can have a big effect on the correlation. If I clear it, I'm back to 0, as I was before. If I have instead 50 points, so there I have 50 points, and the correlation is, well, minus 0, it's 0. The scatter diagram's fairly flat. I will throw in this one, and I'm up to 0.12, and how about giving it a real sense that there's a line going on here, and throwing in that one, and suddenly I'm at 0.2 because now I have this linear trend. So these 2 points at the extremes have a large effect on the correlation. I clear them and I'm back at 0. So when you are looking at a scatter diagram, look at the edges and see if you have 1 or 2 points that might be causing the correlation to be somehow lifted in their direction, as it were. And if you think there are such points, then examine them individually and see how to include them or not include them in the calculation. There isn't a hard and fast rule, and what to do with outliers in particular is a subject where I don't think there's any real agreement in statistics. However, there is agreement about them having a quite large effect on measures like correlation. So we've noticed that outliers can affect R, and we need to be careful. And one last point to note, because we read about correlations quite a lot in journal articles, newspaper articles, and so on, is that if you look at correlations based on averages, you need to be a little bit careful. So here is a scatter diagram that has 1 point. There are 50 points on this. It has 1 point for every state in the United States. And on the horizontal axis is the average reading score on the SAT exam in that state, and on the vertical is the average math SAT score in that state for the year 2011. The SAT is a test that American high school students take to enter college. So there's a reading component and a math component. There is also a writing component, but I'm ignoring that for now. And if you look at the scatter diagram, it is a very tight diagram. It is following a straight line very, very closely. And if you compute the correlation, the number is extremely high. It's 0.97. Now, if the diagram were exactly a straight line, you'd get 1. And this is very, very close. And that's an interesting observation, because this diagram makes you feel that if you knew a student's reading score, so if you knew where they were on the horizontal axis, then you would be able to predict their math score almost without error. That, though, seems very hard to accept. Really, if you are told a student's reading score, would you really be able to predict their math score so accurately? So is the correlation between reading and math scores really quite as high as this? But these points aren't one student at a time, they are a state at a time. There is a point for every state, not a point for every student, and right there we have a problem because states don't take exams. So the individuals on which these variables are being measured are a little bit artificial. It's not the states that take exams, students take exams. So now if I look at the students, and California is just about at 500, it's 500 and 515, so that is California, I believe. Every student in California has been lumped into that point. So if you actually plotted a point for every student in California, they would not all fall in this point, they would fall in a little cloud around that point there. Illinois is pretty high up there. The students in Illinois would fall up here, and if you plotted a point for every student who took this test, then you would get clouds around every point. That is this average point for the state. And the overall picture would be much more fuzzy. The students in each state would be much more variable than their average. And so if the overall picture, when you look at individual students and don't average over states, that picture is more fuzzy, so there is less clustering about the line, and therefore if you look at the scores for students, then your correlation is going to be quite a bit lower than this very high 0.97 that you have by averaging. And what's happened is, again, if you look at students in California, you have taken all the variability in California and you have gotten rid of it deliberately. You have plonked them all down at the average. And by doing so, you have introduced clustering because you have taken away the fuzziness. And so if you see correlations that are based on averages, then think again. What were the units on which the variables should have been measured or could have been measured? Possibly those have a less clear picture than after they have been averaged. Now, we looked at this issue once before when we were doing average heights and we were comparing averages going down, and we said, when you're comparing averages, don't look at the numbers, don't look at the average themselves first. First look at the people, the individuals who are being averaged, and then compare the numbers. It is the same lesson here. When you are comparing correlations, don't look at the correlations themselves first, but look at who are the individuals on which the variables are being measured. And that often gives you an indication of how the measure is going to behave.